Hello, and welcome to Game Revolutions, the series where we pretend the year is 1982 and we write a video game using assembly language. Today, I finally take advantage of an optimization I've been meaning to do for a long time. It's pretty mechanical, doesn't require a lot of thinking, but it will make a lot of my instructions go faster and take up less space. It will also force me to do some reorganization of things, and I can now start using areas of memory that I haven't been able to use before. Also, this may help reduce bugs in the future. What is this optimization? I am finally going to take advantage of the direct page. Cue that chiptune. The 6502 and the even earlier Motorola 6800 offered an optimized way to access some memory called the zero page. On the 6502, if you accessed a 16-bit address with the high byte 0, you could do so with an instruction that's 1 byte smaller and 1 cycle faster compared with other addresses. This is the zero page. The 6809 upped the ante and offered developers an optimized way to access memory on any page, not just addresses with a high byte of 0, but with any high byte. It does this by using the value of the DP register as the high byte, combining that with the single byte from the instruction. This is called direct addressing, and is also 1 byte smaller and 1 cycle faster than extended addressing, which requires the full 16-bit address in the instruction. The catch, of course, is you do have to set up the DP register beforehand, which has to be done in a roundabout way, and which can be expensive. So you probably don't want to be changing what your direct page is too often. Given that load A is the mnemonic whether we're doing direct addressing or extended addressing, how do we actually tell the assembler what we want to do? With many assemblers like LWASM, you can give it a setDP directive. Now this is not an actual 6809 instruction. This will not actually change DP at all. It's merely a promise to the assembler that by the time we get to here, the DP register will have the value C7. And that means that if I went ahead and did an instruction to access a memory location where the high byte is C7, the assembler will just automatically make that be direct addressing. In contrast, if I try to load from some other page, it will know that that needs to be done using extended addressing. And sure enough, in the generated code, if you look at the first load A, it starts at 96, which is binary for the direct addressing load A, and only 42 needs to be in the instruction stream. We don't need the C7 there at all. Whereas loading from 1042 requires the full 1042 in the instruction stream. But I am not going to do it this way. There's a more explicit way which I think will lead my code to be more readable, and hopefully will reduce bugs in the future. Rather than relying on this directive, you can add a symbol just before the address to tell it whether you want it to be direct addressing or extended addressing. It leads to the same result in the binary code, but now you can see in the instruction exactly what I'm expecting. And here's the other nifty thing about this. The other kind of addressing I'm doing, which might require either a number or a label, is immediate mode addressing. And this leads to a policy where I can require in my code I'm either going to do this, or this, or this, before a numerical literal or before a label. Hopefully over time my eyes will get used to seeing this, and if for example sometime I see code that looks like this, I'll think to myself, wait a minute, did I want that to be immediate mode addressing, or is that actually going to be an address of some kind? Leaving off that pound sign is such a large source of bugs in my code. I want to save time, so if I require this of myself, hopefully I will save some time. Before I start my work, I'm just going to capture some baseline performance information first. I have MAME running in overdrive. The meter that's of interest is this meter here in the lower left. It's telling us the average percent of frame that was remaining to be drawn by the VDG by the time I hit the bottom of my loop. A higher number here is better because that means that all of the processing that I've been doing for the next frame finished in a smaller amount of time while the previous frame was rendering. So I'm just going to let this run until the score is about 2600 in celebration of one of my favorite video game systems. And then whatever percentage we see is the one that I'll use as my baseline. Alright, I'm going to call it at 31.8%. The other baseline info that I'm capturing is the size of the code. Right now the last instruction starts at 784F. And I'm starting at 3E100, which is right after the 2 screen buffers. So without some kind of reorganization, I'm very steadily using up the biggest chunk of memory I have, and I'm going to need to expand out to 64K. Hopefully the size of the code will contract a bit after doing this. And also after moving the variables to another location that will be my direct page, something that's maybe much earlier in memory, hopefully I'll be able to win back some space there as well. The first step is complete, and it's about rearranging where things will live in memory. I've decided that my direct page will be here, so all the hex 400s. Normally that's where text screen memory is, but we're not using that. As before, these are my 2 screen buffers, and so right after that 3E100 is still where I'm keeping my code. But I'm also going to move a bunch of my storage into this area here. I'm using a label to keep track of what I'm going to set the DP register to be, but I'm not doing it yet. I'm just defining the label, and I'm using it as part of the org statement so I can ensure that everything I want to go on the direct page will happen here. These are all the variables I'm currently accessing using extended mode, and which need to be used in the mainline loop every iteration. So this is the most important stuff to make as fast as possible. Starting at hex 600 is where I'm putting other storage. These are variables I don't access in the main loop. For example, things relating to animating the car exploding, which only happens when the car gets hit, and also some of my large arrays. So for example, items like the holes in the ground and rocks on the ground are stored in this array of obstacles. I do not use extended mode addressing with this label. Instead, I'll load an index register using immediate mode addressing with that label, and I'll access the array elements and the fields of those elements relative to the X register. So it would do me no good to have this on the direct page, so I'm not going to waste space with it there. So the way things stand right now, the direct page variables don't actually take up that much space. They're starting at 400, and they're only going up to 42F. So plenty of space for more. Meanwhile, these non-critical storage areas, starting at 600, go all the way up to A1C. That means I have a good extra 300 or 400 bytes remaining in that area that I could put more storage. But that's not enough room for these. A huge amount of my memory is spent keeping the mountains or the buildings, whichever one we're currently using, decompressed in memory. I have 2 copies of the background to help with stack blasting. A while back in another video, I talked about how I redid stack blasting by spending a lot more storage, but then gaining a lot more speed. I'll link to this video in the description if you want more information about why. But you'll see it's taking hex 400 for each. So that's a good hex 800 bytes that I'm using just for that. I may end up relocating this somewhere in the larger 32K once I start using the full 64K. But for now, I'm just going to keep this in line with the code. So it's starting at 3E100, and then the code starts immediately after those buffers. So now my last instruction starts at 740A. So I'm already seeing a more efficient use of the memory. I've gained myself a little bit more space at the end, and I have not yet done direct page addressing. I guess I should say that. This is the first step, is just relocating things, reorganizing things, but I am not using direct mode addressing anywhere yet. What I have done is explicitly add the greater than sign everywhere. So I'm doing my new policy. It's either immediate mode addressing or extended mode addressing, and I'm being very explicit about it. So I'm going to try running this now. In theory, nothing should have changed, but I am a little bit worried about using this area and even like the text screen area that's normally used by BASIC. I have not been infringing on their areas before. My hope is that since these areas are not disturbed by the LOADM itself, that the LOADM should work okay. And the reason the LODEM should be leaving those areas of memory untouched is because anywhere I used a ZMB, I turned it into an RMB. ZMB would force zeros to be written into those areas as it loads. RMB does nothing. It's just setting up a label and having the assembler adjust its pointer so that the next label will get the appropriate value. But there should be no effect on running BASIC by having these RMBs in the area of memory that BASIC normally uses. And since my code was expecting those areas to be initialized with zeros, I am now doing that at runtime. So the LODEM will not write any bytes, but as soon as I execute, that's when I'm going to actually start changing that memory. So here's my LODEM. Looks like we're in BASIC. Hopefully I should be able to print something okay. Yes, all right, let's execute. Okay. I'm not surprised. I knew I would be screwing something up somewhere. Here's my idea. I did not have the setDP in here anywhere. I had removed it when I was doing all my work. I originally had it here as a kind of defensive move. I am not accessing any memory in the 8000 range. So by doing this, I will not inadvertently use direct page addressing for any of my loads or stores or anything. Again, since I'm using greater than everywhere, I don't know if this is really going to make a difference, but I got to try it at least. Oh, there we go. Oh, you had me going there for a bit. So I guess that did fix something. Maybe there was some direct page addressing that was inadvertently being used before I was ready. But there's still other problems here that need to be understood. Okay. So trying it with the debugger to see what's going on. Looks like when we hung, we were at a sync instruction. Let's check the disassembly. Disassembly shows us at 8955, but the PC register is 4739. That's pretty unusual. 8955 is an extended color basic in its IRQ routine. I think this is a job for tracing. So I'll set a breakpoint at the very beginning of my code. That's when I'm going to want to start the tracing. Here. And here's my tracing command. It just prints the values of all the registers as well as the disassembly and the source. I'll get my trace off command ready to go. Continue. And here we are stuck. Looks like we're stuck in a different place. Turn off the tracing. So if I go to the very bottom of the trace, it seems like whatever went wrong happened very quickly. So we have this interrupt, and just before that, we were swapping screen buffers, and so we did a sync to wait. Then we got an IRQ. Here's the vector, so we jump to the service routine. And this address tells me we're in disk extended color basic. So we are entering disk extended color basic after I have trashed some of its memory. Disk extended color basic uses the IRQ to turn off the motor. So it does its thing, and then it jumps into extended color basic to do whatever it wants to do with the IRQ. This is probably it's about to change the timer value. Why we would stop right here is beyond me, but clearly this is a problem. We should not be entering disk extended color basic at any point. Is it possible we got halted? So in disk basic, the service routine is getting the value of the timer, which is in the range that I'm probably trashing. We ask if it's 0, and it's not because we did the decrement right after. We store the value back, and now we ask if it's time to turn off the motor. We did not take the branch because we end up right afterward. We load another value, which surely I've trashed, and we use that as our command to the disk controller, and then we go on our merry way. And it sure seems like that's the last instruction we ever got a chance to execute. So I don't know, we're sending bogus information to the floppy. Maybe it did halt us. So let's see, when we program the floppy drive controller, the value of A is A0. That does have the high bit set. That is the halt bit. So we are giving permission to it to halt us. Yeah, I'm gonna guess it's halting us. We cannot continue to do this. I had forgotten about interrupts. So I need to make my own dummy interrupt service routine that prevents us from entering disk extended color basic or extended color basic or color basic for that matter. Total dummy no-op ISR. Hey, it's Dave, editor of the future. While I was working on that bug, I had to stop what I was doing and research how the floppy disk controller works. That is the only reason I had even the smallest clue as to what was going on. And then, while researching that, I decided if I have to learn about this stuff, you do too. And so I shelved that video and the video before so I could work only on the floppy disk controller video. And in fact, there are 2 of them. So if you would like to know what on earth I was talking about and you haven't seen them yet, find the links in the description, and your eyeballs can see the pictures of the thumbnails up here somewhere or other. But now, back to the past. Okay, so here's my fix. On startup, we go here, and it goes to the vector both for the IRQ and the NMI, and it has them jump either here for the ISR or here for the NMI. This just acknowledges the IRQ with the PIA, and then it'll return, and for the NMI, we just return. Okay, I think we're past the point where we were all halted and bad things happened. I think we're good. All right. Are we finally ready to actually start using the direct page? Now we can finally put this label to good use. We're still using it in our org statement to put all of our direct page variables starting at hex 400. But now also, at the very beginning, we use it to set up our direct page register. But that's not all. Check out all the less than signs. The less than signs that say, this friend is on the direct page. And now the last address for the last command is at 735B. I did spot one thing, and it's kind of painful to have to do this. But when I'm doing stack blasting, I am dorking around with the DP register. Depending on how many bytes I'm copying over, many of the variants are using the DP for data transfer. And that means while I'm doing stack blasting, I cannot be using the direct page. So this very frequently used variable, at least at this point in the code, I have to use extended mode addressing. And not only that, but some of these other variables as well. I am going to lose some of the gains that I've given myself, because we just don't have enough registers to satisfy me. And with that change, that moves my last address to 7367. Okay, it's working again. I should be very happy. I'm just kind of disappointed at what I had to do. So let's see what our final perf measurement is. Let's see when our score gets up to around 2600, what the average percent frame remaining will be. All right, I'm going to call it at about 33%. To congratulate folks for making it this far, here is your bonus. I am not going to change the display mode away from the text screen. I'm going to keep the display on the text screen. And what will that do? That will allow us to visually see all of our variables changing as the game moves. We won't be seeing the moon. We won't be seeing the car. We will only be seeing a visual representation of our variables. Oh my, isn't it beautiful? All right, let's try a few things. I'm going to make the car jump. Keep your eye over here. Oh yeah, going up and down, up and down. And over here, you can see that's the background rotational offset, which keeps going up. Now let's fire some bullets. Keep your eyes over here. This one keeps track of how many bullets are in play. And this one is our countdown to let us know when it's safe to add a new bullet. And these are our scores. So as I'm holding down the fire button, I'm probably shooting things. And so our scores are going up. So how did we do? The speed gains were pretty modest, just over 1% of a frame. Honestly, it's pretty surprising that's as good as it got. But the space gains were quite nice. The fact that I was able to take advantage of memory I wasn't using before, and the fact that many of the instructions got smaller, bought us well over 1K before we hit that boundary before RAM and ROM. So that's pretty good. Anyway, I hope you enjoyed. I hope it was interesting to you. It was, as usual, very interesting to me. Thank you for watching.